Question number 21. A wire has an unstretched length of 2 meters and a stress of 1.6 times 10 to the power 5 pascals is applied to the wire, and the new length of the wire is 2.10 meters. The wire obeys Hooke's law. What is the Young's modulus of the wire? So this is a direct question. So we'll be representing the stress as a sigma. So this is a sigma value. The formula for finding the Young's modulus is stress over strain. So sigma divided by the strain value. So sigma is directly given as 1.6 times 10 to the power 5 pascals, and strain is the elongation divided by the original length. So here the elongation you can find out by subtracting the new length minus the original one. So this is gonna give you the elongation. So here it is 2.10 minus 2. So it means that 0.10 meters is the elongation. So here's you need to substitute the 0.1 and the original length, which is 2. So upon calculation, you will be getting 3.2 times 10 to the power of 6 pascals. So the option D is the correct one. Question number 22. What are the SI base units of stress? So just now we have learned that the stress is represented by sigma, and that's basically the pressure applied to the material. So pressure formula is force over area. So here you can convert this force into mass times the acceleration divided by the area. So you're finding the unit of stress now. So you're converting the formula to the units. So the unit of mass is kilogram, unit of acceleration is meters seconds to the power of -2, and the area is meters square. So the remaining is kilogram meter inverse seconds to the power of -2. So the correct option is option B. Question number 23. The diagram shows a force extension graph for a rubber band as the band is extended and then the stretching force is decreased to 0. So this is the graph given. What can be deduced from the graph? So the first option is the rubber band does not return to its original length when the force is decreased to 0. This is the original length, and there is no extension here. The rubber band is in the original length now because here is the extension given. So 0 extension means it's at the original length. So as the rubber band extends, the extension increases. Then as it contracts, the extension decreases. So it comes back to the original length. So the first option is not correct. Then the second one, like option B, is the rubber band obeys Hooke's law for the extensions shown. So this would be the graph if the Hooke's law is obeyed. So here it is the stress and strain graph. It will be the same for the force and extension graph. So if you're having the graph as a straight line, then it's obeying Hooke's law. But here it's not a straight line, which means that it's not obeying a Hooke's law. Then option C, the rubber band remains elastic for the extensions shown. This is correct because it returns back to the original length even though the energy is lost. So there is an energy lost. That's why it's not taking the same path as the rubber band is contracting. So it's having an elastic nature, even it's not correctly follows the same pattern as it goes for the extension. So this is the correct option, option C. And the shaded area represents the work done in extending the rubber band. So always the area is representing the work done. So as it is extending, this would be the work done. So that's a correct statement. So the option C is the answer for this question. Question number 24. Which row is correct for sound waves? So the first column is sound waves can travel in vacuum. It cannot travel in a vacuum, so it could be a no. And can be polarized. No, it cannot be polarized. And it can diffract through a gap. Yes, it can diffract through a gap. So the correct option is option A. Question number 25. A source emits a progressive sound wave in the horizontal direction. The wave travels away from the source in a direction towards the right. So the source is towards the right side. The graph shows the variation of the displacement of the particles from their equilibrium positions with distance from the source at a particular instant of time. The distance to the right of the equilibrium positions as shown are shown as positive. So here the positive displacement is showing the particles are moving to the right side. So the displacements of the particles is to the right. So obviously the negative displacement shows that the particles are moving to the left side, which means that it's away from the source direction. So the position Y represents the displacement of a particle in the sound wave at a particular distance from the source at this instant. So which statement about the motion of the particle is correct? So the first option, the particle is moving away from the source. The particle is actually moving towards the source, because source is over here and the waves is traveling to the right side. So it is towards the source, not away from the source. So if it is too away, it must be going to the right side. So it is option B. Question number 26. Two polarizing filters are placed next to each other so that their planes are parallel. The first polarizing filter has its transmission axis at an angle of 50 degree to the vertical. The second polarizing filter has its transmission axis at an angle 20 degree to the vertical. The angle between the transmission axis of the two polarizing filters is 30 degree. A beam of vertically polarized light of intensity 8 watt per meter square is incident normally on the first polarizing filter. What is the intensity of the light that is transmitted from the second polarizing filter? So you can use here the Malus law. So this is the formula: I is equal to I naught cos square theta. So usually if the intensity, like the initial intensity, the incident intensity is I naught, and I is the intensity of the transmitter light, and theta is the angle between the transmission axis and the plane of polarization of the incident light. So you can find out for the first filtering filter, like first polarizing filter. So here the intensity from the first polarizing filter is gonna be I naught cos square theta, and the incident intensity is given. It's already vertically polarized. So if it is not polarized one, if it is an unpolarized one, the first filter will just make the intensity to half. But here it's the polarized light given, so it is obeying this law. So this Malus law obeys only when the light is a polarized light. So here you can substitute the values. So I naught is 8 and cos square, the angle is 50 degree. So this is the intensity after passing through the first one. For the second one, this the light I1 will be instanting on the second filter. So you can substitute here for the I1 as 8 cos square 50, and the cos square theta, here the theta for the second filter is 30. So after doing the calculation, you're gonna be getting around like nearby 2.5 watt per meter square. So the correct option is option B. Question number 27. A dolphin is swimming at a speed of 16 meter per second directly towards a stationary underwater microphone. The dolphin emits a sound of frequency 122 kilohertz. The speed of sound in water is 1480 meter per second. What is the frequency of sound detected by the microphone? So here the source is moving towards the observer. So it's a stationary observer. So if the moving source and the stationary observer is the condition, the frequency detected will be equal to Fv divided by V minus or plus Vs. So here it is moving towards it, right? That's why you have it as a negative. So the formula is F dash is equal to Fv divided by V minus Vs. So here substituting the values will be 1480 multiplied by 122 divided by 1480, the velocity of sound in water, minus the velocity of the source, which is 60. So this is going to be equal to 123.3 kilohertz. So it's nearly equal to the option D. Question number 28. A student carries out Question number 28. A student carries out a double slit experiment using a laser emitting red light of wavelength of 680 nanometer. The light is incident normally on a double slit. The diagram shows part of the pattern of bright fringes visible on the screen at a distance of 2.4 meter from the slits. The distance across 5 bright fringes is measured as 34 millimeter. What is the slit separation? So this is the double slit experiment. So there are two slits. Here there is a separation and that is represented with A, and the distance from the slit to the screen is represented by D, and the distance between the fringes is represented by X. So there is a double slit equation. You can find out the wavelength by using the formula AX divided by D. So here what you have to find out is that slit separation. So it is to find out the A. So rearranging the formula would be lambda D divided by X. You can directly substitute here for the lambda, which is 680 nanometers, so 10 to the power of negative 9 times the distance from the slit to the screen, which is 2.4, divided by the fringe separation. So here for the 5 points, so there are 1, 2, 3, 4 X values, right? So that 4X is equal to 34 millimeters, so 10 to the power of negative 3. So X will be equal to 34 times 10 to the power of negative 3 divided by 4. So you can do it separately and substitute, and the value after calculation will be equal to 1.92 times 10 to the power of negative 4 meters. So the correct option is option C. Question number 29. The diagram shows a stationary wave on a stretched spring at an instant in time. So here is the picture. So it's a stationary wave given. Two particles on the spring P and Q are shown. Which statement about the vibrations of P and Q is correct? So here the first one, they have different frequencies. No. Since it is part of a single wave, it has the same frequency. They have the same amplitude. No. They have the different amplitude. So the first point P has this much of amplitude, but the second one has less than that. They have different period. No, because if the frequency is the same, the time period is also going to be the same. Then the D option is they are always in phase. That is a true statement. So option D is the correct answer. So the particles between nodes are in phase. Like in phase means they move together, while the particles in different segments can be out of phase. So here, since it is a stationary wave, these are representing the nodes. So the P and Q are the particles between the nodes. That's why they are in phase. Question number 30. Green laser light passes through a diffraction grating and forms an interference pattern. The diffraction grating contains 400 lines per millimeter. The wavelength of the laser light is 550 nanometer. What is the highest order of diffraction maximum produced by the grating? So the formula for the grating formula is d sine theta is equal to n lambda. So d is the distance between the slits, so the slit separation. So here, for using the formula, you need to find out the d value, and d is always 1 divided by n. So here you need to find out the n value, the highest order. So if you are rearranging it, it will be n is equal to d sine theta divided by lambda. So here you do have the wavelength, you have the n value to find out, and what you need is the theta. And it's given that the highest order of diffraction, and the highest order means the theta is always of 90 degree. So if it is theta 90 degree, sine theta will be equal to sine 90, and that is going to be 1. So this equation again changes into d divided by lambda, which means that 1 over n multiplied by lambda. So you can substitute here 1 divided by 400. It's in millimeters, so you can change into meters. So it's 400 multiplied by 10 to the power 3 multiplied by the lambda value, which is 550 times 10 to the power of negative 9, and that's gonna be, after calculation, 4.54. So it's nearly equal to 4. So the option A is the correct one.